What is consciousness? In simple terms, consciousness is awareness of existence, of seeing, feeling, and thinking. It's the inner realm where memories, sensations, and feelings combine to generate the feeling of you. Yet, even though everyone knows what it feels like to be conscious, defining consciousness is, and how it arises, is one of the biggest secrets in science and philosophy. Sometimes the problem has been called the hard problem of consciousness, a label coined by philosopher David Chalmers. According to Chalmers, the hard problem asks, how can brain tissue consisting of brain cells and chemical messages generate consciousness such as agony, joy, or a chocolate chip cookie? It's one problem to understand how information is processed in the brain, but a whole different problem to understand why such processes have any sort of sensation at all. To begin peeling at the problem, let's begin with the brain, one crowded complex web of about 86 billion brain cells, each communicating with several thousand surrounding brain cells. The brain cells converse with one another with tiny electrical messages, generating activity patterns representing everything you see, feel, or do. Try to visualize a city at dusk, with lights flashing off and on in concert, each for a unit of information. That's the brain's electrical waltz. Scientists have mapped sections of that waltz to specific mental processes. For example, the brain's visual cortex interprets what you see. The brain's sound-sensitive cortex interprets sound. The brain's prefrontal cortex handles thinking and deciding. But while we can plot out which regions of the brain become active for a specific activity, this doesn't yet answer why these processes appear in the sensation of living. Why does brain electrical activity yield consciousness and not a dead, mechanical feeling? The consciousness problem has vexed minds for centuries. Ancient Greek philosophers such as Aristotle and Plato debated the character of the soul and its existence apart from the flesh and blood of the body. In the 17th century, René Descartes proposed a famous theory that mind and body were two entities, an idea known as dualism. According to Descartes, the mind, or consciousness, was non-physical and communicated with the body through the brain. Though dualism is no longer in fashion with modern science, it raises a significant question. Is consciousness non-physical, or is it a purely brain function? One theory that keeps minds rumbling is integrated information theory, IIT, which holds that consciousness arises through integration of information in a system. The more complex and integrated a system, the more conscious it will become. In this theory, the brain's complex web of neurons creates a sort of awareness no individual part could possibly coordinate alone. Another theory is panpsychism, a school of thought that consciousness is an integral property of the universe, a property such as space and time. According to this theory, even quantum particles have a kind of awareness, and the brain is a sort of mechanism that takes and enables that awareness to become rich and deep, awareness of a kind we know and enjoy. The case thickens when one takes in consideration the brain's ability to yield enormously disparate consciousnesses. For example, dreaming. During sleep, when an individual is in a state of REM, the brain invents rich real-life experiences out of thin air, blending reality and imagination. Meditation. By being present, humans can manipulate our sense of time, ourselves, and even our sense of pain, and unveil how consciousness can be remapped. Brain injury. Locked-in syndrome patients are conscious but cannot move and cannot speak, trapped in their heads. And then, of course, there are extraordinary instances, such as a patient waking out of a coma and describing rich experiences, a patient having near-death experiences, floating, seeing a light, an incredible feeling of peace. All these events blow apart our view of where consciousness resides and works. Exploring consciousness forces us to confront life's most profound questions. If consciousness arises out of the brain alone, then what does that mean for our sense of self? Do we simply exist as complex machines with no deeper reality? Or is there a transcendent in the mind, something that betrays a deeper connection to the universe? Philosophers, too, have reservations about free will whenever consciousness enters the picture. If our minds and choices arise out of brain activity, then are we in control or passive observers of activity in our midst? And then, of course, there's artificial intelligence. Can machines develop consciousness? Today's computers can pass tests with ease, but it doesn't have a feeling of inner life. In case one could one day mimic the brain's complexity in a computer, could it ever have a sensation? Or is consciousness a property specific to life? In the 19th century, a deep question entered the minds of scientists. Can life have developed out of lifeless matter? One of the most enduring and early hypotheses is that of the primordial soup, proposed by Alexander Oparin and J.B.S. Haldane in the 1920s. Envision a planet Earth, a tremendous pot filled with a rich brew of water, gases, and minerals. That soup wasn't your ordinary soup. It was churning with potential. The atmosphere of early Earth was a whole lot different from present times. Instead of oxygen, it is probably filled with gases such as methane, ammonia, hydrogen, and water vapor. Energy, such as lightning, volcanic eruptions, and ultraviolet sunlight, pounded at the mixture, shattering molecules and allowing them to reform in new, unexpected forms. Scientists Stanley Miller and Harold Urey in the 1950s took a shot at testing this theory in a laboratory. They took early Earth's conditions and filled a flask with them, mixing gases and electrifying them with sparks in an attempt at simulating lightning. In a week, amino acids, precursors to proteins, had accumulated in the flask. That it was a startling breakthrough, proving that life's simple ingredients can arise out of dead matter, was a real jaw-dropper. But amino acids are only the tip of it. For life to occur, these simple compounds must have been organized into complex forms, such as proteins, then nucleic acids, and then cells. How it all happened is one of science's greatest unsolved mysteries. While the theory of primordial soup gazes at Earth's face, a new and exciting theory turns its eyes to the ocean's depths. Envision hydrothermal vents, submarine geysers spewing out warm, mineral-charged water from the ocean floor. Around such vents, supported by skyscraper-thick rock chimneys, is a bizarre environment in which water, heat, and chemicals combine. In the 1970s, deep-sea pioneers discovered under astounding conditions a thriving community surrounding such vents. Life forms such as tube worms, clams, and shrimp, living in a part of the ocean with no sunlight. Instead of photosynthesis, these living organisms employed chemosynthesis, a mechanism for life to gain its energy from chemicals such as hydrogen sulfide. The discovery changed our thinking about life's origin in life. Hydrothermal vents may have provided a safe, high-energy environment in which life could have begun. Heat and chemicals spewed out by such vents could have powered organic molecule genesis, and rock walls of vent chimneys could have provided a natural scaffold in which such molecules could have crystallized into complex structures. Some researchers believe that life's building blocks evolved in little, enclosed spaces deep in such rocks, in which chemicals could react over and again and again. Over a period of long ages, these early reactions could have evolved into early self-replicating molecules, precursors to DNA and RNA. The heart of life holds a deep question. How did molecules first begin to reproduce? Today, DNA is such a molecule, storing genetic information, but it cannot function in its absence, and proteins cannot form in its presence. This chicken and egg problem challenged scientists to coin the RNA world hypothesis. RNA, a less complicated cousin of DNA, has one remarkable characteristic. It can store information and act as a catalyst for chemical processes, much like proteins. Having both traits makes it a strong potential for the molecule that jump-started life. Imagine a time when early RNA molecules floated about in early oceans, accreting and sometimes altering. These mutations could have generated new abilities, including the ability to form simple structures or utilize energy. Over millions of years, these early RNA systems could have evolved into life's complex genetic machinery that exists today. But life, or at least the beginning of life, could have begun somewhere in the universe, not on planet Earth, according to panspermia theory. According to the theory, life could have fallen down to our planet from outer space, and its precursors could have reached our planet through collisions with meteorites, comets, and asteroids, which have been found to have organic compounds aboard. A particularly famous example is the Murchison meteorite, which crashed in Australia in 1969. Chemists studying the meteorite uncovered amino acids and other organic compounds locked inside of it, evidence that life's ingredients can reside in outer space. And if these molecules could make it through in a trip to planet Earth, then could have seeded the planet with life's ingredients. The theory raises an intriguing question. If life's ingredients traveled to planet Earth in outer space, could life actually reside in other regions of the universe? Looking for life in outer space is, in many ways, a sequel to our quest for life's origins. The origin of life is not a scientific issue, but a shared narrative that brings us together with the universe. It encourages us to recall the astounding complexity and wonderfulness of life and the delicate balancing act between chance and necessity. Philosophically, the issue of life's origin encourages us to question our place in the universe. Do we represent a cosmical fluke, a chance chemical reaction? Or is life an inevitable consequence of the universe's laws, doomed to arise whenever and wherever opportunity arises? When we're thinking about the universe, it's natural to picture what can be seen: glinting stars, whizzing galaxies, and planets that orbit them. For centuries, these observable wonders were regarded as representing all that existed. Ancient astronomers gazed at the nighttime sky, mapping out constellations and taking in its beauty, unaware that they were skimming the tip of a much larger picture. Let's begin with what we know: ordinary matter. It's matter that forms everything seen and touched: stars, planets, trees, and even you. It consists of atoms, tiny constituent parts that combine in limitless combinations to form the matter that's around us. In each atom, a nucleus of protons and neutrons is surrounded by an electronic cloud, all kept together with the powers of nature. But then comes the mind-boggling fact. All of this, the atoms in galaxies, oceans, and mountains, is only 5% of the universe. It's a humbling realization to know that all that can be seen is part of what actually is. Invisible, 95% of the universe cannot be seen with eyes, trapped in shadows to be discovered yet. Imagine yourself walking through a wood with a windy day. You can see leaves shaking and feel wind in your face, but can't detect the air at all. Dark matter is a lot similar to such invisible wind, a matter that doesn't radiate nor reflects light, but whose presence can't be argued with. Astronomers first encountered the idea of dark matter when studying galaxies in the 1930s. Something seemed off. Galaxies were moving at such high speeds, according to all logic, that they must have flown apart. Apparent stars and a seen gas simply did not have enough gravitational pull to maintain everything in its proper position. Something seemed to be holding galaxies together, an invisible mass that could not be measured. That invisible mass was called dark matter. Dark matter acts in much the same way a cosmic scaffold works, providing an understructure onto which galaxies and clusters of galaxies form. Remove it, and the universe in its present state could not work. In spite of not yet knowing what dark matter is, many believe it is composed of exotic particles such as WIMPs, weakly interacting massive particles, or axions. Others have yet more unorthodox theories, such as primordial black holes. Whatever its form, dark matter makes up 27% of the universe, working in quiet harmony to bind together the web of the cosmos. If glue that holds the universe together is dark matter, then a force unmaking the universe is dark energy. Imagine inflating a balloon, seeing it expand steadily in all directions. Imagine, in contrast, that in lieu of decelerating at slow pace when the balloon disperses, the balloon begins inflating at ever faster velocities. That's an acceleration in expansion, one that astronomers discovered in our universe in the late 1990s, and one that changed our view of cosmology overnight. Dark energy is thought to make up 68% of the universe, and it's the largest and most elusive ingredient in the cosmic mixture. It's thought to cause the universe to expand, but no one knows what it is. Some think it's a property of vacuumed-out space, a vacuum energy that strengthens with an expanding universe. Others think it's a field that permeates the universe, or a sign that gravity isn't a complete theory yet. The implications of dark energy are profound. If expansion of the universe continues to speed up, one day we could have a big freeze, with galaxies moving so far apart that the night sky will be dark and barren. Dark energy could reverse, and then the universe will have a big crunch and will fold in on itself. In any case, dark energy holds the key to the universe's fate. The cosmic mixture isn't just a scientific problem, it's a challenge for philosophers to understand our role in the grand scheme of life. Dark matter and dark energy remind us of our ignorance, inviting us to see beyond our field of vision. Dark matter and dark energy remind us that the universe is much weirder and more beautiful than we ever imagined. Consider this: what if dark matter and dark energy have nothing to reveal about life? Do they have a connection to consciousness's origin, even to laws of physics governing reality? Secrets that bridge science and philosophy, and whose questions have puzzled minds for centuries. Do we have a multiverse with other cosmic recipes creating totally different realities? Is the universe finite or infinite? What is the multiverse hypothesis? The multiverse theory proposes that our universe, our reality, is not alone but one of many. All these universes, together they form a multiverse, could possibly extend infinitely, with each one living its own life, like pages in a book in outer space. It's a concept that sounds out of science fiction, but it naturally arises out of a group of theories in cosmology and physics. The multiverse tests our understanding of reality at its core. For centuries, we have considered the universe singular, all-encompassing, but when we have broadened cosmology, fractures have developed in that assumption. What if the universe is simply a small balloon in an infinite ocean of balloons, with its own individual reality in each? One of the first and most fascinating proposed proofs for the multiverse comes from quantum theory, the part of physics that deals with the behavior of particles at a micro level. In the 1950s, physicist Hugh Everett developed the many worlds interpretation to try and understand an oddity in quantum theory. Particles appear in a variety of states at the same time, even when not being measured. It's in a state of superposition. The concept, according to Everett, was extreme. In any quantum event, the universe branches out. Let's say a coin is flipped. In one universe, it's heads. In another, tails. With the many worlds interpretation, both occur in alternate parallel universes. It branches off into an infinite web of realities, creating new ones all the time. If Everett is correct, then in a universe out there, there could be a version of yourself who made a different choice at a key point in life. Someone familiar, yet one who lived a whole different life. The multiverse, too, comes out of theory in cosmic inflation, explaining how the universe increased in a burst of rapid expansion in seconds during and following the Big Bang. Imagine inflating a balloon, with each puff a spurt of energy creating space. In theory, regions of the cosmos may have expanded at a variable rate, producing discrete space bubbles. Each bubble a universe unto itself, with its laws of physics and constants. Some could mimic our universe, and others could be radically alien. There could even be a universe with a new, powerful gravity, brighter lights, and life in forms yet undreamed of. The bubbles in the multiverse theory say our universe is one of many, floating in a sea of creation infinite in its breadth and depth. It's a head-shrinking reality. The enormous universe out there can be but a speck in a much larger, unimaginable reality. The multiverse is backed, too, in a theory out of string theory, a model attempting to merge all of the universe's forces of nature. String theory supposes the universe is made of incredibly small vibrational strings of energy, and it requires a universe with many dimensions, many, many more than the three that we perceive in our ordinary lives. In string theory, the arrangement of these extra dimensions determines a universe's physical character. With near limitless forms of shaping these dimensions, string theory predicts an enormous landscape of conceivable universes, each with a specific character. Some scientists think our universe is but a single point in this gigantic landscape. Others could have a different behavior of particles, a wacky flow of time, or wholly new forces governing reality. While the multiverse is theoretical, there are fascinating indications that it may actually exist. For example, the cosmic microwave background, CMB. That background radiation glow, a relic of the Big Bang, is a sort of early universe fingerprint. Certain anomalies in CMB have been proposed as possible signs of contact with alternate worlds. Mathematics of elegance. Equations of quantum theory, strings, and inflation naturally generate the multiverse theory. Not direct evidence, but in that these theories consistently fit together, it strengthens the assumption that many realities must exist. Simulation theory. In case our universe is a simulation, not a theory many philosophers and scientists have considered outlandish, it's possible that infinite other realities exist, run by sophisticated entities or entities. The theory of multiverse challenges not only physics but even philosophy, and our concept of reality and our place in it must adapt. Do we have a duplicate? In a multiverse, there could be infinite you, each with a variation. One could have taken a different career. One could have lived in a universe in which Earth did not form. It raises profound questions about individuality and identity. With infinite yous, who are you then? Do we have a higher purpose? In the case of life in many worlds, life could mean that life isn't an accident, but a predetermined consequence of the universe. On the other hand, in case some worlds don't have life, it brings into sharp relief just how extraordinary and fragile life in our universe could be. What can we know? The multiverse brings into reality the finite character of our knowledge. Can we ever hope to understand them, assuming that there are worlds out beyond our telescopes? The multiverse puts humanity in its proper position, suggesting reality possibly being enormously larger and weirder than our minds can perceive. What is time? Time is one of the most basic parts of our lives, yet one of the most elusive. We see it as a constant progression, moving steadily towards the future, yet backwards towards the past. Seconds become minutes, and minutes become hours, and days pass unobtrusively into memory. But what is time, actually? Is it an unending river, hurtling us down its current, or is it deeper, more elusive, perhaps even an illusion? For centuries, humans have struggled with such questions. Philosophers, scientists, and poets have attempted to define it, yet its actual form continues to defy simple answers. From controversy in days gone by to present-day physics, time continues to resist simple examination. To most, time seems one way, in a sequence of past, present, and future. We recall the past, live in the present, and look to the future. This is a reflection of how we organize our lives, from our daily routines to our narratives about our lives. Yet our consciousness of time isn't as simple as it seems. For instance, picture how time can vary according to your feelings. An hour with a loved one can pass in an instant, but an hour in a queue can drag out forever. This seems to say that our consciousness of time is not simply in the hands of our minds, but of events too. The scientific theory of time changed in a fundamental way in the early 20th century, courtesy of Albert Einstein and his theory of relativity. Einstein proved that time isn't a constant, a force universally agreed upon. It's relative, a function of factors such as velocity and gravity. Imagine two persons, one motionless on Earth and the other traveling at near the velocity of light in a spacecraft. According to Einstein's theory, time for the person in the spacecraft would pass more slowly relative to that of the one in motion on Earth. That observation, a prediction of Einstein's theory, has been confirmed through tests with the use of atomic clocks aboard high-flying aircraft. Einstein's theory predicted, too, the theory of space-time, a four-dimensional tapestry in which space and time merge into one. In such a theory, time isn't a river in motion, but a dimension, a height, say, or a breadth. All points in space occur at one instant, and all times, past, present, and future, can all occur together in a block universe. In such a universe, the flow of time is an illusion, and the present, experienced, is merely a moving consciousness in a static timeline. Though Einstein's theory revolutionized our cosmology for time, quantum reality presents a problem altogether different from Einstein's theory. On a small enough scale, particles follow a behavior that seems to challenge our commonsensical view of time. In quantum mechanical terms, particles don't have a specific sequence of events. Instead, particles occupy a state of superposition, with many alternatives together, in a state of until measured. That raises profound questions about causality and whether, in fact, time, as we have a commonsensical view of it, even holds in quantum reality. Some physicists speculate that time could emerge out of deeper laws, laws that transcend time, just as temperature emerges out of molecule motion. According to such a view, time could be a useful tool for describing the macro universe, but not necessarily a fundamental reality. Philosophy has long questioned the reality of time, and one of its most enduring debates concerns whether time is real or an illusion. Ancient Greek philosopher Parmenides argued that change is an illusion and reality is timeless, with all times present together at once. This theory chimes with modern physics theory of the block universe. Other schools of thought, represented by philosophers such as Heraclitus, argued for constant flux in time, stating, "You cannot step twice into the same river." This view reflects our common experience of time as changing and in flux. In the 20th century, Einstein's theory of time was challenged by philosopher Henry Bergson, who argued that physics could calculate time mathematically, but could not grasp its lived reality. For Bergson, time was not a sequence of static instants, but a continuous, flowing reality, a theory he termed duration. The elusive nature of time isn't merely theoretical. It has real consequences and touches our lives in surprising ways. The twin paradox. Two twin siblings, one of whom flies into deep space at near light velocity and stays for a period, and one of whom stays behind on Earth. On return, the spacefaring twin will have aged less, a real-life consequence of time dilation. Time travel. Often relegated to science fiction, but some hypotheses for Einstein's equations imply that time travel could actually work, at least in theory, but an awful lot of energy will be needed. Perceived time. Research indicates that time seems to pass more slowly during an emergency, for instance, or when one is in deep focus, as more detail is processed in the brain, creating a perception of prolonged time. Broader consequences and philosophical relevance. Considering the nature of time encourages one to wonder about one's position in the universe and about existence. Time and free will. If all moments coexist in a block universe, then must our choices be determined? Do consciousness and consciousness alone grant us the agency to mold the future, even in a frozen timeline? These questions complicate our concept of free will and accountability, time and mortality. Our perception of life's fragility is closely involved with time. The realization that moments pass and cannot be recovered imbues them with value, prompting us to appreciate the present. But if time is an illusion, could life and its memories be eternal in some manner? Time and the universe. If time is a creation of the universe, then what was present before time started? And when the universe ends, what happens to time? These questions strain the limits of humanity, opening both wonder and humility. Black holes are regions in space in which gravity is so strong that nothing, not even light, can escape. It's an image of a star that's enormously massive and dense, with a gravity that's unescapable. Because of that, such a star will cave in under its own gravity, creating a black hole. The center of a black hole holds a point called the singularity, in which matter is compressed into an infinitely tiny place. Outside of the singularity, there's the event horizon, a boundary even matter can't cross and escape from. It's a black hole whispering in the ear of the universe, "Step over, and forever I have you in my grasp." Black holes don't consume everything in a vacuum, indiscriminately sucking in whatever comes its way, as one might picture them to be. No, they curve and distort spaces nearby with gravity, similar to any larger body will. What's different is in space-time's curving, creating a gravity that's a gravitational pull, so strong even the universe's flesh will fold under and about them. The development of black hole theory can be traced to 18th century British physicist John Michell, who proposed dark stars with gravity strong enough to trap light. But publication of Einstein's theory of general relativity in 1915 saw black hole mathematics unfold. The math predicted that immensely massive entities could distort space-time in much the same manner a massive sphere can distort a sheet of rubber when placed on it. Even Einstein, though, questioned whether such extreme entities actually could exist. It took physicist Carl Schwarzschild to first calculate Einstein's mathematics, proving black holes to be a math reality. For decades, black holes only existed in theory until Cygnus X-1, a powerful X-ray source, in the 1960s, a sign of a black hole devouring matter out of a neighboring star. Black holes occupy center stage in modern astrophysics today, and in fact, have even witnessed a glimpse of one, a photograph taken in 2019 of the supermassive black hole at the center of the galaxy M87, captured in a shot taken with the Event Horizon telescope. The event horizon is most fascinating about a black hole. It's not a boundary in the same sense a membrane is, but a boundary in space-time. Once one is past it, all routes go inward. Time and space become twisted in such a way that laws of physics, at least in a way in which we comprehend them, stop working. Imagine an astronaut being drawn towards a black hole. To an observer in a distant position, an observer, that is, not with a direct view, in a position such that any observation is purely radiative, the astronaut will slow down when near the event horizon, redder and dimmer and dimmer and redder, until its vanishing act. For an astronaut, however, time will pass in a perfectly normal manner until one reaches the singularity, when gravitational attraction approaches infinity. What happens when one is past the event horizon? That's a question that science is not yet capable of answering. There's a theory, for instance, that the singularity stores all information about matter devoured, and a theory that black holes can serve as portals to other regions in space-time, or even to alternate universes. Black holes are not all of a uniform kind, but vary in size, with each having its individualistic attributes. Supermassive black holes. Hiding in the heart of galaxies, including our Milky Way, these monsters have a mass between 1 million and 1 billion times larger than our Sun and are regarded as responsible for shaping galaxies. Intermediate black holes. Evasive and less detectable, these black holes fall in between stellar and supermassive black holes in terms of behavior and size. Primordial black holes. Hypothetical black holes that could have been present in the first fractions of a second following the Big Bang. If present, they could reveal information about early times in the universe. A most fascinating black hole is Sagittarius A, our Milky Way's supermassive black hole at its core. Invisible, but its presence is revealed through nearby stars' motion, hurtling at dizzying speeds under its influence. Another famous black hole is Cygnus X1, a black hole that has been under investigation ever since its discovery was announced publicly. By tracking matter it accretes from its companion, astronomers have uncovered significant information about black hole behavior and its influence on its environment. Perhaps most sensational events surrounding black holes involve a merge, in which two black holes merge and become a single, larger black hole. Black hole merge events produce titanic releases of energy in gravitational waves, rings in space-time, first detected at the LIGO laboratory in 2015. Black holes are not only a wonder for scientists, but a source of profound and deep questions about reality, about time, and about existence in general. What happens to information? One of the greatest black hole mysteries is the information paradox. What happens when matter enters a black hole? Do its makeup details simply vanish forever? Information can't be destroyed according to quantum theory, but black holes violate that principle. Some theorists speculate information could be etched onto the event horizon or escape in Hawking radiation, a faint glow proposed by Stephen Hawking. Are black holes portals? The theory that black holes can serve as portals to other dimensions has captured both public and scientific imagination. Wormhole theory speculates that black holes can span distant regions of space-time, creating a shortcut through the universe. Pure conjecture, but one opening wondrous questions about interstellar travel and reality's shape. Black holes and the nature of time. Time behaves in a wacky and unpredictable way near a black hole. As you approach the event horizon, time will start to slow down compared to an observer outside and will eventually not move at all. That flies in the face of our traditional view of time as a constant flow and speculates that it could be less rigid than we have understood. Do black holes contain the key to unlocking time's secrets? In 1950, physicist Enrico Fermi asked a famous question: where is everybody? It occurred in a discussion regarding the odds of intelligent life in outer space. With an incredibly large number of stars in the universe, many with planets, it almost seems a dead bet that other civilizations must exist. And yet no sign of them can be detected. This paradox, high odds of extraterrestrial life and no sign of them, is known as the Fermi paradox. The paradox can actually be dramatized in a thought experiment. You're in a large woods and can hear birds singing, leaves moving, and a distant cry of animals in the distance. But imagine, in these woods, nothing but silence. The universe is the same, full of planets and stars. So then, why don't we have any echoes of an echo of a civilization? Reasons for hope in hunting for life include finding exoplanets, planets that orbit a star outside our solar system. For centuries, worlds apart, existed only in theory, but in the 1990s, astronomers spotted them with high-tech methods. One of the most striking techniques is the transit technique, in which a planet blocks its star, and a faint dimming of the starlight happens. That faint shadow reveals about the planet's size, its path, and even about its atmosphere. So far, over 5,000 planets have been confirmed, and many of them fall in the habitable zone, that region in a star's vicinity in which life's haven, water, could possibly survive. Worlds such as Kepler 452b and Proxima Centauri b have become key foci for hope in terms of a homestead for life. With each new discovery, one can't but recall that our little planet is but one small planet in a universe full of potential. The Drake equation. Astrophysicist Frank Drake in 1961 crafted a simple yet potent equation to estimate the number of communicative, active civilizations in the Milky Way. The Drake equation considers factors such as the rate of star formation, proportion of planets with a star, and chance for life to develop and become intelligent. We don't yet have values for many of the variables, but at least the equation sets a basis for thinking about probabilities. With even conservative estimates, math reveals that life could be a widespread presence, but prevalent, and yet we haven't seen any sign of it. Good reasons for not having seen any alien civilizations yet range from disappointing to sensational and include, they're too distant. The Milky Way is a big 100,000 light-year breadth, and even assuming that civilizations' distances between them and us could be unbridgeable. Signal communications at light speed could arrive years out, taking a decade, 100,000 years, even 1,000,000 years to make it. They're hiding. Perhaps sophisticated civilizations have heard of us, but don't choose to make contact. That's the theory of the zoo, that planet Earth is an exhibit, seen but not visited. They've all wiped out. Civilizations develop, flourish, and become extinct long before we can possibly detect them. Cosmic events, self-inflicted or natural events, could destroy them before even seeing them. We're looking in the wrong spot. Our search methods could be too narrow. Most approaches, such as search for extraterrestrial intelligence, SETI, rely on listening for radio waves, but technology could use unimagined approaches in aliens. We're Saul. It's also conceivable that life, and even intelligent life, is vanishingly rare. Earth could be a cosmic aberration, an oasis in an otherwise desolate galaxy. The nature of alien civilizations. What if intelligent extraterrestrial civilizations exist? What could they be like? Do they resemble humans, or will they be incomprehensibly different? An exciting theory is that of Type 1, 2, and the 3 civilizations, a part of the Kardashev scale, with a measure of a civilization's level of technological advancement in terms of its use of energy. Type 1 uses all the energy on its native planet. Type 2 harnessed its whole star's energy, possibly in structures such as Dyson spheres. Type 3 wields energy at a galactic level, having unimaginable capabilities. Humanity, in contrast, isn't even a full-fledged Type 1 civilization yet. Meeting a Type 2 or Type 3 civilization would be for ants to encounter humans, one that's an encounter so asymmetrical it could possibly not make any sense to us at all. Though a lot of attention is focused on intelligent life, less complex life could actually be ubiquitous. Microbial life could occur on planets and moons with oceans below the surface, such as Europa or Enceladus, or in thick atmospheres of exoplanets a long distance away. And even here, on our planet, life's proven to have a lot of chutzpah, thriving in nasty environments such as in hydrothermal vents, in acidic lakes, and in polar ice. These examples serve to remind us that life's capabilities are enormous, and it can occur in environments that we regard as hostile. Are we exceptional? The search for life in the universe puts our perception of humanity's purpose in the universe to the test. In the case of being alone, it accentuates life's singularity in our planet and our responsibility to protect it. In case of not being alone, then it can mean that we have a larger, shared cosmological narrative in the universe. What does it mean to be intelligent? The presence of extraterrestrial life, whether microbial or complex, would require a rethinking of intelligence. Do emotion, creativity, and culture specifically in humans or in a different form in outer space? In the real world, we're conditioned to have things behave in predictable fashions. A rolling ball rolls in one direction. A clock moves in a relentless sequence, one tick at a time. But in the quantum universe, particles seem to obey a whole different set of laws, almost a dreamlike reality. Perhaps one of quantum's most astonishing and bewildering phenomena is wave-particle duality. Attempt to visualize light, a warm shaft of sunlight through a window. For centuries, scientists debated whether light is composed of particles or waves. Was it a stream of minute particles, insisted Isaac Newton, or a wave-like motion, insisted Christian Huygens and others? The answer, it turns out, is both. Light behaves sometimes as a wave, radiating out and interfering like waves in a pond. But light behaves sometimes as a particle, delivering its energy in discrete packages called photons. The duality isn't restricted to light, however. Electrons, tiny particles that orbit a nucleus in an atom, exhibit a wave-like behavior too. In the famous double-slit laboratory experiment, electrons were shot through a barrier with two slits. Instead of creating two sharp spots on a sheet of paper in back of the slits, they produced an interference pattern, a sign of waves. Yet, when scientists inserted detectors at the slits to observe electrons, wave-like behavior stopped and electrons exhibited particle-like behavior. The experiment reveals a fundamental fact. Observation changes how particles behave. It's as if nature prefers to exhibit only one face of its coin when under scrutiny. Another strange quantum behavior is superposition. In contrast to the classical world in which objects have one location at a time, quantum particles have many at once. Think of a coin in spin. Before it lands, it's both heads and tails, a state of uncertainty, a superposition. In quantum reality, particles can have a similar state of uncertainty. An electron, for example, doesn't orbit an atom's nucleus in a planet or the sun sort of configuration. Instead, it's a cloud of probabilities, only choosing a specific position when measured. The principle is dramatized famously through a thought experiment conceived during a dream by physicist Erwin Schrödinger. Imagine a cat in a sealed box with a poison-filled vial that will discharge poison when a quantum particle behaves a certain way. Until the box is opened, the cat is dead and alive at the same time, a state of uncertainty, a superposition. The paradox highlights the strange, dreamlike nature of quantum reality. Perhaps quantum mechanics' most surreal phenomenon is entanglement. Once two particles become entangled with one another, their state is linked, no matter the distance between them. Change one, and the other happens instantly, even over vast distances, to change two. Albert Einstein famously likened it to spooky action at a distance, appearing to defy a fundamental principle that nothing can move at a velocity higher than the speed of light. Yet experiments have consistently proven that entanglement is real. One way to try to visualize entanglement is to use a pair of gloves. If a left glove is found in one box, then at once you can know the other glove will be in the other one. But in quantum terms, it's as though the gloves don't make a determination about whether it's a left glove until the box is opened. Until then, they're in limbo, both left and both right, simultaneously. While quantum mechanics is a slippery concept, its laws underlie much of today's modern technology that surround and serve us, including transistors and semiconductors. computers, and smartphones rely on quantum principles to regulate the flow of electricity. Laser, from laser-guided missiles to fiber optic communications, quantum mechanics is at work in lasers. Quantum cryptography. By exploiting quantum laws of entanglement and superposition, quantum cryptography can provide unmatched security for communications. Quantum computing. Unlike computers, traditional computers utilize binary, ones and zeros, to compute information, while quantum computers utilize qubits, capable of taking a position in a state of superposition. That allows them to compute complex computations at unprecedented velocities. What is reality? Reality comes under challenge in quantum mechanics. If particles can be in many places at one time and can have many states, then what does that say about existence? Is reality a single, definite one, or one constructed through observation? Some physicists believe reality could be an inherently probabilistic one, a universe of possibility that takes shape only in measurement. That theory blurs the boundary between observation and observer and opens up the possibility that consciousness could actually have a role in defining the universe. The universe is information. Quantum mechanics has led some to speculate that the universe is not made of matter and energy, but of information. In this view, reality is a big cosmologic computation, and particles bits of information. This theory raises profound questions about existence and whether or not the universe could even be a simulation. Secrets of quantum and free will. The indeterminism of quantum mechanics, its hesitation to give definite answers until observation, has free will implications. If reality in the universe is based on probability, not definiteness, then doesn't that mean that our choices can't be determined? Or could quantum uncertainty simply serve to cover for a deeper, concealed determination? Dark energy is a mysterious force that brings about accelerated expansion in the universe. To understand its significance, one must go back in time to the early 20th century, when scientists knew that the universe was static, not growing and not shrinking. But in 1929, astronomer Edwin Hubble noticed something extraordinary: distant galaxies moving away from us, and the further, the farther. What he saw at that point confirmed that the universe was actually growing, like the balloon's surface growing when it inflates. Scientists took for granted for years that gravity, a force drawing matter, will slow down its expansion at one point in time. But two groups of scientists in the 1990s discovered in parallel, unaware of one another, a breakthrough. By studying light derived from distant supernovae, they discovered that expansion of the universe wasn't decelerating, but rather accelerating. That astonishing observation hinted at a force working in a counter-direction to gravity. Dark energy. Dark energy forms about 68% of the universe, dominating all ordinary matter and dark matter combined. And yet, no one knows what it is. Several hypotheses have been discussed, each offering a glimpse of the face of elusive force. Albert Einstein first proposed a cosmological constant in 1917, a value added to his general theory of relativity, in an attempt to model a static universe. After Hubble's expansion discovery, Einstein abandoned it, declaring it the greatest blunder. But theory re-emerged when dark energy was discovered, and it could work to represent constant force for accelerated expansion. The cosmological constant theory speculates that dark energy is a property of space, and that when space expands, it creates additional space, and with it, additional dark energy. The theory holds together observations, but creates a deeper issue. Why is space filled with this energy, and how did it arise? The alternative theory is that dark energy isn't constant, but dynamic, one of a field, a form of quintessence that varies through time. Unlike with the cosmological constant, quintessence would rise and fall and vary with the universe. It could mean dark energy's influence could become stronger or weaker in the future, altering the fate of the universe. Some theories are that our current theory of gravity isn't finished yet. Dark energy isn't an additional force, but a sign that gravity is different at a cosmological level. That theory demolishes Einstein's theory of general relativity, and new physics could be in store for describing the universe's behavior. Dark energy not only guides the present, but holds its deepest secret, that of the universe's fate. Depending on its character, the universe could have one of a range of possible ends. If dark energy continues to drive expansion eternally, galaxies will move apart, stars will exhaust their fuel, and the universe will become cold and dark, a fate referred to as the Big Freeze. Over trillions of years, even atoms could disintegrate, with an empty universe full of feeble radiation and particles. In some theoretical models, dark energy's effect strengthens over time. In such a scenario, the force responsible for tearing the universe apart could become even more powerful and overwhelm all else, disintegrating galaxies, stars, planets, and even atoms. This destructive fate, the Big Rip, would mark a violent end for space-time itself. If dark energy grew weaker, even reversed, gravity could win out and cause the universe to fold inward. Galaxies would collide and merge, temperatures rise, and the universe could suckle into a singularity, a fate termed the Big Crunch. According to theory, such a collapse could give rise to a new Big Bang, creating a cycling universe that expands and collapses forever. Though a theoretical presence, dark energy's effect can be detected and measured. Perhaps one of the most direct observations comes from observations of the cosmic microwave background, CMB, a faint glow of the early universe that lasts long after its birth in the Big Bang. That radiation takes a snapshot of the early universe, and its patterns verify the presence of dark energy. Another significant observation comes in observations of galactic scales, and these confirm that the universe's expansion changed over time. Spacecraft such as the Hubble Space Telescope and future James Webb Space Telescope can penetrate deeper into the universe, searching for information about dark energy's nature. Though such breakthroughs have been gained, dark energy is an incredibly challenging beast to study. Dark energy doesn't radiate light, react with matter, and produce a direct signature. Instead, its presence must be inferred through its presence in the universe, a challenge that takes creativity, accuracy, and collaboration. The nature of reality. Dark energy throws our reality into doubt, suggesting our universe is stranger and more complex than ever imagined. If most of the universe is invisible and immaterial, then can we say that we know our role in it? Are we merely discovering deeper layers of reality? The fragility of knowledge. The discovery of dark energy puts in perspective that scientific knowledge is not a constant. What we have long regarded as a complete picture of the universe proves to be part of a larger, complex narrative. That humility is a challenge and an encouragement, a challenge to persist in doubting and searching. Humanity's role in the cosmos. Dark energy also raises profound questions about humanity's role in the universe. If we are part of a universe designed by powers far in excess of our current comprehension, then in what way can we respond to it? Do we have a moral imperative to preserve the fragile planet that is our habitat, knowing that it is an extraordinary oasis in an ever-expanding vacuum? The Great Filter Theory, proposed in 1996 by economist and philosopher Robin Hanson, aims to answer the Fermi paradox, the fact that life in the universe seems likely but invisible. In a nutshell, the theory of the Great Filter postulates that there is a barrier, some incident or challenge, that stops life from developing into high-tech, spacefaring species. The barrier could occur at any point in the life timeline of a species, anywhere between emerging life to sending colonies to other planets. If the great filter is in our past, then we have overcome the most difficult steps already. But if it is in our future, then humanity may have yet to encounter survival threats that will seal our fate and seal humanity's fate in the long run. The first potential location of the great filter is at the beginning, transitioning life from dead matter to living matter. On Earth, life started 4 billion years ago under unpredictable and hostile environments. Nobody knows precisely what kind of process saw the first life-emitting, self-replicating molecule, but hypotheses such as the theory of primordial soup and hydrothermal vent theory postulate that life took a specific, infrequent mix of chemistry and environment. If life emerging is an incredibly improbable chance, then perhaps not seeing any sign of high-tech civilizations can be understood, and we simply inhabit a rare exception, a lucky winner in a universe full of lifeless planets. Once life emerges, it must become increasingly complex. For 4 billion years, life on Earth was simple, single-celled life forms. For a long 4 billion years, life on Earth took a simple, single-celled form. The transition to multicellular life, a key development towards becoming complex, happened only 600 million years ago, relatively recently, in the life of Earth. This transition may require specific and atypical circumstances, such as stable environments, ideal nutrition, and an avoidance of catastrophic events. If complex life is a relatively rare phenomenon, then many planets will have microbial life, but go no further. For even with complex life, intelligence is not necessarily a given. Dinosaurs ruled the planet for 150 million years and produced no sophisticated tools or civilization. It took a series of chance events, mass extinctions, changing environments, and genetic mutations to make primates into humans. But even intelligence is not enough. Species must have the ability to modify the environment and generate technology. With no tools, smart life can become locked to its planet, inactive to explore the universe or leave a detectable mark. Here, then, is where the great filter is most unsettling. If the barrier to advanced civilizations is surviving technological breakthroughs, then it could mean many species destroy themselves before ever reaching the stars. Humanity's rapid development has brought unprecedented achievements, but unprecedented danger. Nuclear weapons, global warming, pandemics, and artificial intelligence form a short list of threats that could make humanity destroy itself. This stage of development is sometimes a crucial bottleneck in which civilizations have enormous impediments in order to survive at all. If most civilizations fall at this stage, then it could explain the quiet of the universe. The universe could be full of shells of civilizations that reached for greatness and killed themselves with their inventions. Even if a civilization can navigate technological peril, it will have to overcome the tremendous barrier of colonization and exploration of space. To go to nearby star systems requires extraordinary wealth, energy, and creativity. For example, the nearest star system, Alpha Centauri, is over 4 light-years away. With current technology, it will take tens of thousands of years to arrive. Overcoming such distance could include breakthroughs in life support, energy, and propulsive technology. If interstellar travel is too costly or cumbersome, then civilizations will remain in a state of confinement, never exiting its native planets. The Great Filter Theory confronts us with uncomfortable questions about our presence in the universe. Do we stand for an outlier, having already overcome the filter? Or is the filter in our future and must face obstacles that will seal our fate? If the filter is in our past, then we must have been incredibly fortunate, a species having survived the most improbable obstacles. That will make life on Earth even more cherished, a sole source of complexity in an otherwise barren universe. But if it is in our future, then it is a sign of alarm. Humanity must move with caution through technological peril and ensure that we're not yet another quiet society in an infinite universe. Are we alone? If the great filter is at the beginning point, at life starting out, then we could, in reality, actually be alone in the universe. This aloneness will have a humbling and profound effect, a reminder of life's uniqueness and fragility on Earth. The responsibility of intelligence. As an intelligent species, we have the potential to shape our future for ourselves. The great filter pushes our will, urging us to act responsibly, prioritize long-term survival at the expense of immediate gain, and collaborate to counteract existential threats. The search for meaning. The quiet of the universe prompts us to search and comprehend our place in the universe. Whether we actually find other civilizations in searching, we're united in larger purpose, a shared curiosity and wonder that supersedes borders and years. The moon is Earth's sole satellite, and one of the most singular distinguishing aspects of our nighttime sky. It's a quarter Earth size and orbits at an average distance of roughly 384,000 kilometers. It stabilizes the tilt of our planet, forms our tides, and even controls the pulse of life. But the moon is not a mere satellite. It's a time capsule with messages about the early solar system and tumultuous events that molded our planet. Scientists and philosophers have long debated several theories about the origin of the moon. Let's review the most salient ones. One of the first and oldest such theories is the fission theory, in which the moon is proposed to have been part of Earth at one point in time. According to one such theory, a whirling Earth ejected a portion of its mass, which, over time, developed into the moon. Some argued in its favor, citing that the composition of the moon is similar to that of Earth's crust. The fission theory, however, carries several weaknesses. First, Earth must have spun at an impossible pace for such a thing to have happened. What's more, such a violent expulsion of matter would have etched a scar on Earth, one that doesn't exist in our present times. A theory, the capture theory, postulates that the moon developed somewhere else in the solar system and subsequently was captured in the gravitational field of our planet. That could be a reason why a few moons in the outer solar system, such as Neptune's Triton, have unorthodox orbits. While intriguing, this theory is not without its weaknesses. In order to capture an object as massive as the moon, a very specific combination of velocity and gravitational forces must have taken place. The near-circular smooth path of our moon suggests a model of origin that is not similar. The theory of co-formation proposes an origin for the Earth and Moon in the same cloud of gas and dust in early days of the solar system, and it holds together with many moons of gas planets, including Jupiter and Saturn. But even this theory cannot yet address why the moon is a little differently composed than Earth. For one, the moon doesn't have certain compounds of volatiles, and this would suggest a decidedly different path of origin. The best supported theory today is the theory of a giant impact. According to this theory, approximately 4.5 billion years ago, a planet approximately Mars in size, sometimes called Theia, crashed into a youthful planet Earth in a catastrophic collision. The impact would have been unimaginably violent, enough to vaporize Theia and a significant portion of Earth. Debris in the impact careened off in space, and a disk of molten rock and gas formed about planet Earth. Over time, this cooled and condensed into a moon. The moon's composition is strikingly similar to that of Earth's mantle, lending strong support to the theory that it condensed out of material drawn out of Earth. The Earth-Moon system holds a high angular momentum in agreement with a model for a giant impact. The impact could have tilted Earth's axis and give us the seasons that we enjoy today. Current simulations of an impact yield a result astonishingly similar to today's Earth-Moon system, lending further legitimacy to the hypothesis. The moon is not a passive spectator in the stagecraft of Earth's history. It played a deep role in shaping our planet's development. The moon's gravity holds Earth's axis in a constant position, fending off extreme fluctuations and keeping them from creating unpredictable fluctuations in the climate. That consistency has made life possible in relatively predictable environments. The moon's gravity creates tides, and tides have conditioned life on Earth for over 4 billion years. Tides may have been responsible for life's origin, providing early life with a mechanism to migrate to land from seas. The moon's gravitational force introduces a slow, braking action to our planet over countless ages. On early Earth, days were relatively short, only a matter of a few hours long. That deceleration over many ages granted us our 24-hour day. The fragility of cosmic coincidences. The presence of the moon brings into sharp contrast the delicate interplay between chance and necessity in the universe. If Thea's impact were a little less, a little more, at a somewhat different angle, simply, the moon probably wouldn't have existed or could have been altogether unrecognizable. That raises deep questions about chance in creating the universe. The moon in human culture. The moon has for centuries filled humans with wonder and awe. It guided sailors, kept track of time, and spawned countless myths and fables. From early calendars with a lunar basis through modern-day poets, the moon brings humanity together with the universe on a deep and intimate level.